Come to our last lecture, which is going to be in electronic form. As you can see, it's going to be covering the topic of discrete probability, which is our second lecture about discrete probability. Yes, so let me first make sure that you can see the slides. So, can you see the slides?
Yes, doctor.
Thank you. So last time we introduced the very notion of probability, which just measures the likeliness of a certain event to occur. But we need to have a clear description of that event in our heads before we can measure its likeliness. So that event needs to be properly described, precisely described, and we need to know to which space does that event belong. Today we are going to talk about probability theory, which is just a very gentle touch to the topic. It won't dive deeply. So we are going to, most of this stuff written here won't be covered. So we will be getting to know about assigning probabilities and the complements of events and their unions, their intersections, their independence. And we will be visiting the notion of conditional probability because it motivates the upcoming discussion of Bayes' theorem. So let's first start with the notion of so when you have a coin and you flip that coin, so the probability that it's going to give you heads is 1/2, and it's going to give you tails is 1/2. That's when the coin is fair. So naturally occurring, it's 1/2 for each possible event, for each possible outcome of the experiment. What if we want to impose our own preferences, to interfere with that naturally occurring distribution of probabilities? So heads is giving 1/2 and tails is giving another 1/2. So they both sum up to 1. But what if we want to interfere? What if we want to impose our own preferences? So in the previous lecture, we talked about the possibility of designing a biased coin so that when you flip that coin, it doesn't give you heads with probability 1/2 or tails with probability 1/2. So it gives you, it's more biased to one of the choices. So what do we call this? And what is this situation generally called? This is called assigning probabilities. So we are not leaving the experiment to just provide us with probabilities as we repeat the experiment, just like a die cube, which has 6 sides and 6 numbers consequently. So if you just throw it, you are going to see one number, one of those 6 sides, 6 facets, with probability 1/6. And that's what common sense would tell you, and that's what naturally occurring things would let you know. But what if we want to interfere with that? So that's what's called assigning probabilities. So and what do we call this? We call this coming up with probability distribution. So in the end, all the events must have a probability which sums up. Their probabilities must sum up to 1. That's just like a general law we have to follow. But what if we, just like the example we discussed in the previous lecture, what if we design a coin which gives you, it's biased so that heads come up twice as often as tails. So heads, as you flip it, they would show up twice as often as tails. If someone who is a coin making expert, if he asked you, if I want a coin to do with that, to produce such outcomes twice as often as tails, how shall I process that coin? And what would be the probability of heads? What would be the probability of tails? So for a fair coin, we know that it's going to be half-half. But for this biased coin, we know, we were told that they want it to be twice, that the heads show up twice as much as tails. So what should that imply? It would imply that since we have the probability of heads plus the probability of tails should be 1, then you can simply substitute using this little formula here. And this would give you the fact that the probability of heads would be 2/3. So the probability of heads being 2/3 and the probability of tails being 1/3 is called a probability distribution. And apparently it is different than the classical probability distribution of 1/2, 1/2. What about a uniform distribution? A uniform distribution is similar to the classical case, where the coin is fair, and similar to the classical case, where the die cube is fair. It's similar to the very, very unlikely case where all the students have the same grade, which is very unnatural. So uniform means unified. So everyone is giving the same probability to occur. So for n elements, each element has a probability to occur 1/n. So yeah, that's just a reminder that what if your probability involves multiple events? So for all those events, so like a major event E, which constitutes of sub-events, and each sub-event is represented by the element belonging to a set S. So for all such elements belonging to S, so we just sum up the probability. That's just very intuitive. It should come up straight out of your mind without much thinking. So here, consider this example that we made a die cube, but it's not fair. It's designed so that it is biased, that it would give 3, the number 3, twice as often as each other number. So the other numbers are just fairly treated. They have the same probability, but 3 has twice as the others. Twice the probability as the others. It's more often likely to show up. So what is the probability that an odd number appears when we roll the die? Yeah, we have the answer, but let's think of it, step by step. So we are asking about the odd numbers to appear. The odd numbers are 1, 3, 5, and what about 7? 7 is not on any facet of the die. So 1, 3, and 5. And 3 occurs twice as often as the others. So let's count the portions. How many portions do we have? What's the probability for 1 to appear? Who would like to answer this? Generally, for a fair die, for 1 to appear is like for any other number to appear. Which is 1 over 6. So the portion is 1 for each facet, and the sum of portions is 6. So here we have 1 over 6 for 1, 1 over 6 for 2, 1 over 6 for 3, 1 over 6 for 4, etc. But here, in this twisted example, since 3 appears twice as often as any other number, so the number of portions is not 6 anymore, it's like 7. It's not like 7, it is 7. But in those 7 portions, 1 has only 1 portion, so 1 over 7. 2 has 2 over 7. 3 has 2 over 7. So all the numbers have 1 over 7, except for 3, which has 2 over 7. I hope this is clear. Who thinks it's still miserably? Who thinks it's clear as mud? I mean, it's not clear at all. Okay, that's pretty quiet feedback. So let's see for our major event, which is 1, 3, or 5, the set of odd numbers to appear. 1 has a probability of 1 over 7. Also 5 has the probability of 1 over 7, but 3 has the probability of 2 over 7. That would be 1 plus 1 plus 2 divided by 7, which is 4 over 7. What about the complements of events? So if they tell you, I mean, you can revisit this example here and modify it so that it asks for the even numbers to show. So the even numbers are the opposite of the odd numbers. What would be the probability for even numbers to appear? Can you give me an answer quickly on the run? What would be the probability for even numbers to appear as you roll the die? Any idea? That would be 1 minus 4 over 7, which is 3 over 7. Okay. What if you have multiple events? And those events have something in common. For odd and even numbers, a number is never both. But here, you just imagine a situation that you have something in common. So the probability that event 1 union event 2 occurs, so they like both occur. It's the probability that the first occurs plus the second occurs minus the probability of the intersection to occur. Why? Because we just don't want to double count the intersection. It's the probability that you selected a student whose major is math plus a student whose major is computer science, and you just excluded students who's doing a double major. Yes. So a quick visit to the topic of conditional probability, which is about I will let you know that I've got something already there. Is this going to narrow down your search space? Is this going to narrow down your probability space? It's like telling you in advance that I will be selecting students only from the Faculty of Electrical Engineering and Information Technology. So it's not a university-wide selection. So first, you just look at this simple formula, which tells you that the probability that event E happens given that F has happened already is just the union of those two events divided by the probability, the probability of the union of those two, the probability of the intersection of those two events divided by the probability of the second event. So here you have E and F. E is the probability you are worried about. You are just questioning what is the probability that E happens. But E is not happening independently. E is conditioned on F. It is somehow linked to F, where F is another event. Well, this is best understood by an example. Let's consider this example first. What's the conditional probability that a family with 2 children has 2 boys? Given that they have at least 1 boy. So given the fact that they have at least 1 boy, this would narrow down my search space. So let's consider all the combinations of having 2 within your offspring. So a family has 2 either boys or girls or a combination of both. So it's either boy boy or boy girl or girl boy or girl girl. That's all the possible combinations. But here they are telling me something. They are telling me that they have at least 1 boy. So girl girl would be excluded from my search space. So here we are talking about boy boy, boy girl, and girl boy. So the notion of conditional probability introduced a narrow down of my search space. And that would be, I mean, if you just apply the definitions we know, the probability, the event that we have a boy boy would be, which is represented as BB, which is what the problem is asking about. The probability that they have 2 boys. That's what we are asking about, boy boy. And F tells me that they have at least 1 boy. At least 1 boy includes boy boy, boy girl, and girl boy. So let's consider their intersection, which is just boy boy. And given our search space, our major search space of 4, you just divide the probability of the intersection by the probability of the given condition, which is F. The probability of the intersection is the probability of boy boy, which is just 1/4, divided by 3/4, which is just 1/3, which is a high probability. Let's go back to this example. I know some of you were already traumatized from bit strings and counting them, but this is a small example of 4-bit string generated at random so that each of the 16-bit strings, 4-bit string means a bit string of 4 digits of 4 bits. So this is of length 4. What's the probability that it contains at least 2 consecutive zeros, given that its first bit is a 0? So we don't really, we don't really have a big example here. I mean, it wouldn't be much of a headache to just count them. So a 4-bit string contains, how many 4-bit strings are there? 2 to the power 4. And how many bit strings? Let's consider the following event, which is the bit string contains at least 2 consecutive zeros. How would I count such bit strings containing at least 2 consecutive zeros? Any idea? So the textbook says that you just manage them manually. But how would you count them? I mean, do you have any hint? Do you remember that nice formula connecting the number of bit strings to Fibonacci? I am not telling you to use it here. I mean, you'll be like using. Thank you, Yazid. I mean, it's at least it's better than nothing. It's just to have a little bit of thumbs up. But the point is that you can do it manually here. You don't need to use all the mathematical techniques you learned, whether you remember them or not. So you just imagine those bit strings which have at least 2 consecutive zeros, and they were listed here, and their number is 5. So their probability is 5/16. So those which start with 0, how many bit strings out of all the 16-bit strings, how many of them start with 0? Half of them. I mean, generally for an n-bit string, generally speaking, for an n-bit string, we've got 2 to the power n possible bit strings of length n. Half of them start with 1, and another half starts with 0. So in this case, we've got 8 out of those 16 starting from 0, starting with a 0. So here you will be dividing 5/16 divided by 8/16, which is just 5/8. The 16s cancel out. Yes. It's possible for 2 events to be independent. That is, one of them does not affect the other. So whether we were talking about bit strings or other objects, the probability of their occurrence can be completely independent of another event to occur. So consider the following example here. I mean, let's first say, when can we say that they are independent? For 2 events E and F, when can we say that they are independent? They can be said to be independent when the probability of their intersection is just the product of their probabilities. And as an example here, you just consider E to be the event that a randomly generated bit string of length 4 begins with the 1. So we just generate a random bit string of length 4 and it begins with a 1. Can you tell me how many elements are in E? Come on. That's 16/2, which is 8. Okay, and let F be the event that this bit string contains an even number of 1s. Are E and F independent? If the 16-bit string, if the 16-bit strings, sorry, of length 4 are equally likely. So first we have 8-bit strings representing the event E. Because as we said, half of them begin with a 0, half of them begin with a 1. But let's consider those which have an even number of 1s. So they can be enumerated in a small subset like the one there in the slides. So an even number of 1s means 2 1s, 4 1s. So 4 1s is just all of them are 1s. 2 1s can be, you know, exchanged here and there. Altogether having 4. Altogether summing up to 4 possible combinations of bit strings. So 4 divided by the whole search space, which is, sample space, that would be 4/16, which is just 1/4. That's the probability of the intersection. So what about having them even? And what about having them, having an even number of 1s? And what about having those starting with 1? Those starting with 1 are 1/2. And an even number of 1s is also 1/2. This would remain your little homework to count them. If you multiply them, that would be 1/2 multiplied by 1/2, which is 1/4. And the probability of their intersection is also 1/4. So here we have equality, which just matches the definition of independence. As you can see here in the definition, we have if and only if, which means that the notion of independence is equivalent to this, the occurrence of this formula. Okay. And here is the example of boy, girl again, with a modified question, of course. So consider the event E that a family with 2 children has 2 boys, and the event F that family with 2 children has at least 1 boy. Are those 2 events independent? Who would like to vote? Are they dependent or independent? Who would like to suggest an answer? Well, they are dependent, they are not independent, because one of them would cause the sample space to shrink. So, and you can also verify that by the fact that the product of the two probabilities, probability of E times probability of F, is 3/16, whereas the probability of their intersection is 1/4. 1/4 is not equal to 3/16. It's a tad higher. Okay. A very quick visit to Bayes' rule, Bayes' theorem. I would just like to let you know that, why is this very useful, and to which part of probability does it belong? It belongs to conditional probability, and it helps you make inference. It helps you infer what could have happened given the following outputs. It helps you, it has countless applications in, as mentioned here, in medicine, that is like computer-aided medicine, or AI-aided medicine, or machine learning that is involved in making medical decision support systems. Law, which is a very wide umbrella term. Artificial intelligence, engineering, very broad terms. And for us, cybersecurity, spam filtering, predicting what could happen based on certain inputs, predicting the attacker behavior, and so on. And artificial intelligence is very, very wide umbrella term. It just keeps growing, as you can see. And one major component of it is machine learning. And of course, it is heavily based on probability and conditional probability. So if someone was tested to be COVID positive, is he or she necessarily actually sick with COVID? This may or may not be the case. What if he or she was tested negative? He or she could be actually sick. Actually, they do have the disease. So Bayes' theorem allows you to make sort of inferences in such situations. Here is what the theorem states, and here is a small example, and we won't be going any step deeper beyond that. So if you have a sample space and you have two events, E and F, taken from that sample space, so the probability that F occurs given E is just this fraction, this huge fraction, with certain mathematical assumptions, just to guarantee that the denominator is not zero. You're not dividing by zero. So the probability that F occurs given the occurrence of E is just the probability that E occurs given the occurrence of F multiplied by the probability of F and divided by this huge denominator, the probability that E occurs given F multiplied by the probability of F plus the probability of E occurs given the complement of F multiplied by the probability of the complement of F. So it's a huge theorem. And I just intentionally removed the slides mentioning its derivation, just not to stretch your material further. And I just opted to take this example, which is about having two boxes. We have a box which contains 2 green balls, 7 red balls. So this box has more red balls. And we have another box which contains 4 green balls and 3 red balls. So it has less red balls. Someone selects one of those two boxes. We don't know which box. So one box was selected at random, and a ball was taken out from that box at random. If that ball was a red ball, what is the probability that this person selected a ball from the first box? So what is the probability that it was the first box which got selected? So we just design our events here. So E is going to be the event that Bob, which is the person, has chosen a red ball. And F refers to the event that Bob has chosen the first box. So by Bayes' theorem, we've got the following computations, which is left to you. But as you can see, since the first box has more red balls, then it is more likely that it was the first box which was selected. So it's 0.645. That's almost 65%. Okay. So that wasn't only the last slide. Let's stop here. Stop the recording. So the recording would stop here.